Good afternoon. On behalf of Engineers Australia, welcome to our first Thought Leaders series for 2024. Today, we'll be talking about geosynthetics and ESG compliance in mining. My name is Amanda and I'll be your host. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional custodians of the country throughout Australia and recognises their continuing connection to land, waters and community. We pay our respects to them, their cultures, and to elders past, present and emerging. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Geofabrics. Geofabrics has been in the business of geosynthetic engineering and building key infrastructure across Australasia for over 40 years. Operating in various sectors with expertise in road, rail, coastal, waste, defence and mining, they aim to help their clients deliver and maintain infrastructure by minimising risk and increasing value through the innovative use of geosynthetic product solutions. Geofabrics has supported the Australasian infrastructure sector on significant projects, from the Victorian level crossing removal to APLNG in Queensland to the Christchurch gondola in New Zealand. On these projects, and every project they undertake, they have a singular focus to protect, contain and secure the physical environment for future generations. Today, we will hear from two speakers, followed by our live audience Q&A. And as always, I encourage you to send questions through to our speakers via the chat box. I'd now like to welcome our first speaker, Darren Webb. Darren is a civil engineer with more than 20 years' experience in waste containment in the mining and other sectors. This includes significant experience related to design and construction, using geosynthetics, including related to management of mine waste and liquor, stormwater and facility closure. Darren has led numerous projects in Australia, Asia and the Middle East, combining technical excellence and the use of geosynthetic materials to help deliver more sustainable outcomes for the environment. Please welcome Darren Webb.
Okay, thanks, Amanda. Let's just start with an acknowledgement. WSP acknowledges that every project we work on takes place on First Peoples lands. We recognise Aboriginal and Torres Strait Islander peoples as the first scientists and engineers, and pay our respects to our elders past and present. So just the agenda of this presentation, we'll just have a little bit of a run through a background on mining and ESG, and then discuss geosynthetics and sustainability and their link to ESG, and then move into a bit of commentary around designing with geosynthetics and geosynthetic material specification and quality assurance, and then finish with some project examples and a summary. So mining. So obviously mining is a fundamental requirement for the functioning of modern society, and obviously mining results in significant disturbance to the environment, including hydrology, hydrogeology and ecosystems in the vicinity of the site. So these impacts are associated with numerous components, but in the context of this presentation, the extraction of mineral from the ore and disposal of and storage of hazardous liquors that might be associated with that extraction, and storage of tailings, which can also be hazardous depending on the process that they've been through. The heap leach stacks, which again are also often have hazardous liquids percolated through them, and overburden and waste rock storage. So mining and ESG. So to maintain a social licence, miners must manage impacts from mining in a manner which meets societal expectations. And that comes from different angles, but particularly ones that you're regularly dealing with the regulator, from financiers and shareholders, and particularly some of the large pension funds are quite active in this regard. And as I'm sure most are aware, there's increasing focus on ESG and sustainability in recent years, and that's particularly in the context of the mining industry, driven in part by some past industry behaviours which perhaps have been not quite meeting society's expectations. So geosynthetics. Geosynthetics are manufactured synthetic materials used for engineering applications, typically manufactured on a sheet and delivered on a roll. That bottom photo shows a roll of geogrid. And the types of geosynthetics you most commonly will be dealing with are geomembranes, geotextiles, geonets, GCLs or geosynthetic clay liners, geogrids, and then there's erosion control mat, turf reinforcement, and many more. I understand Ryan's going to provide a bit more of an overview of the different products, so I won't expand any further in this presentation. But I guess the message is there is lots of different types of geosynthetic materials, and it's not just geomembranes and geotextiles, which are perhaps the most commonly known or the most commonly used. So, mitigation of mining impacts in geosynthetics. So, to mitigate impacts to the environment from mining activities, it typically requires engineering measures to be developed. And geosynthetics can obviously play a role in that. And this includes for applications such as lining systems for solid and liquid, and solid often refers to tailings. And it's worth noting that lining systems for tailing systems help reduce seepage, but can increase the liquefaction risk, and that has an impact on embankment design. The embankment needs to be appropriately designed with or without a liner. It does change things, or it can change that risk profile. Capping systems, so at the closure stage particularly, closing of tailings facilities, waste dumps, etc. Drainage and filters, ground improvement, stormwater management, and of course many more. So geosynthetics and sustainability. The use of geosynthetics enables construction of liner systems with much lower permeability than naturally occurring materials, which typically means clay, and probably more importantly, in areas where clay is not available. So it helps enable these type of activities to occur relatively sustainably in areas where that may not have been able to be done otherwise. So due to their thin and engineered nature, they can offer benefits over conventional construction materials, which are typically quarried, clay, stone, sand, etc. And those benefits are that it's easier to transport. You need ultimately less material because of the engineered nature of geosynthetics. And then associated with that, reduced resource usage and reduced disturbance to the environment, less need to open up, borrow areas, import material from quarries, etc. And then, as a result of all of that, reduced greenhouse gas emissions. So designing with geosynthetics. Similar to any other engineering material, the design must be undertaken with appropriate rigour. And in the case of geosynthetics, that means particular focus on durability, chemical, which is typically linked to the exposure conditions. What are the geosynthetics required to contain, and UV and temperature. Obviously, higher temp applications are more challenging. So, and forces during construction and service. So this is obviously a easily damaged thin material, and it's got low interface strengths. So in simple terms, it can be a slippery material. You need to design often for veneer or slope stability failure along that interface. And then specifying the material properly. all geomembranes aren't the same, all geotextiles aren't the same. Different materials, different products have different properties, and that needs to be considered for the design. What does your design actually need? Mining applications often involve challenging service conditions, and often, more challenging than other applications. And that includes storage or containment of very low or very high pH materials, such as those associated with heap leach activities, bauxite residue, which you're dealing with acidic and caustic materials respectively in those applications. Any other material that might have a high contaminant load, hydrocarbons, salts, metals, other chemicals, and PFAS is obviously a consideration. Exposure to high temperature or UV. And the reality is, usually in these type of challenging applications, you're dealing with a mix of those service conditions. So high temperature, high UV, and acidic material containing other contaminants as well. So it's not you're generally dealing with multiple challenges. And as a result of that, exposure conditions are almost always site-specific, must be considered as such in design. So just because something worked on another site in a similar situation, it doesn't mean that that same product will work on your site, where the ore might be different, the processing approach might be slightly different, etc. And different materials obviously perform differently under different exposure conditions. And the material selection and specification is critical. So how do you help manage that? Well, there's industry guidance for geosynthetic specification, and the Geosynthetic Institute publications are the most commonly used, but they are not developed to suit challenging applications typically of what you're expecting in the mining industry, or for many other industries that you might be dealing with in geosynthetic design. There's an excerpt from GRI GM3 there, which is the HDPE GSI specification, and you read that first sentence. This standard specification is intended to ensure good quality and performance of HDPE geomembranes in general applications. What's a general application? It's open for debate, but most of the time when you're working in the mining industry, containing a hazardous material would not be categorised as a general application. So you need to be very careful about using that specification. Similarly, relying on advice from a supplier is solely on advice from a supplier is risky and generally not recommended. Suppliers should and often do know their product very well and know a lot of information about their product, so it's definitely worthwhile liaising with a supplier during the design stage. But each application is different, and the supplier doesn't know the design intent. The supplier's role is to ultimately sell a product, and that the designer must be aware that that's the supplier's role. I know we're presenting with Geofabrics in this presentation. Geofabrics have a lot of very good information that they can help with the design, but ultimately the designer must ensure appropriate material is specified to suit the application and the design life. The supplier is not taking on the risk of that material not performing as intended. So how do you do that? To assess whether a geosynthetic material may be expected to perform as intended, you can look at the properties of the material used in manufacture, so PE, PVC, polypropylene, polyester, etc. You look at how they, based on research and other publications, how it might be expected to perform in the exposure conditions based on what you know about them. But most often, for these type of applications, you really need to consider doing independent durability testing. This type of testing should be undertaken using samples of the actual products proposed for use. So the actual geosynthetic product, the actual geomembrane product type that's proposed, not just a HDPE geomembrane the product that is intended for use. And typically you might subject 3 or 4 or 5 products to the testing, so you can help identify the best product and also maintain a competitive market for the tender process. And then the testing should be done using methodology that imitates the exposure condition, so using a sample of the actual exposure liquor, the liquor that the material is going to be subjected to, and using an experienced laboratory that is possibly independent. Like if you're running a test on a suite of products from different suppliers, it's perhaps not appropriate to use the Geofabrics laboratory because there's potentially a conflict of interest there. I'm not suggesting Geofabrics would do anything like that, but it's in those situations it's obviously best to use an independent laboratory to avoid that perception. And ultimately, that testing should be done in coordination and scope with the designer and scope to suit the application. It's very important that one type of durability testing may not be appropriate for a different application. And then assessment of the results can be quite complex. The designer needs to be involved in that. And there's multiple properties that need to be considered, and it can be quite complex. So once you've gone through that process to identify the product that you want to use, then you need to specify it in your design, and that would include QA and QC measures in that specification. And typically there's 3 components to that QA QC regime, and that would include manufacturer's quality control or MQC testing, and that's testing done by the manufacturer prior to shipping, routinely done as part of the geosynthetics industry. Every manufacturer does it. It will be available to the designer to check. And then independent quality control testing. So this is the second step that's done by the owner or designer prior to installation. So sampling of the material either prior to shipping or prior to after delivery to site prior to installation. And that helps confirm the material is what the owner is paying for, the properties are what the design needs. You might ask, why do you need to do that when you've got the MQC test results? You might be targeting different properties than what is covered by the MQC testing. And look, experience has shown that sometimes the MQC test results can have limited reliability. There's been situations where things have been picked up in the IQC stage that are different to what the MQC test results have indicated. So it's reinforced the benefits of doing that stage of testing. And then when you get to installation, construction quality assurance. So that's basically monitoring of the installation to ensure compliance with the design. So checking that it's deployed and welded in a manner that meets the requirements of the design, so that you're going to get best use of that material in the service condition. And so for higher risk applications, that construction quality assurance often includes a full-time on-site role performed by a party independent of the contractor, and often that is a representative of the designer. And then after the installation, you can undertake a liner integrity or leak location survey to ultimately check for defects. So that's specific to geomembranes, and its efficacy does vary depending on the application and the site conditions, but it can be quite a useful step. But ultimately, all of those QA/QC measures must be included in the design document, so prepared by the designer. So just now moving on to some applications from some of our recent work. And so this first one involves storage of an acidic mine process liquor, and this is approximately a pH 1 liquor, so very nasty. And the design for this was prepared by another party, but it included a dual HDPE geomembrane liner system. The design was a little bit limited as far as the specification and QA/QC measures that were included in it. It was constructed, it was filled, and after the first fill, it was assessed to be leaking unacceptably. So the owner then dewatered it and undertook a repair regime, filled it again. Very quickly, it was leaking unacceptably again, and then dewatered again. And this has all happened within 1 to 2 years of completion of construction. So you can imagine there was a rather frustrated owner. So they called in WSP to have a look at the geomembrane after the pond had been dewatered for the second time. What we observed was numerous weld failures, primarily associated with extrusion welding, and we inferred that to be associated with poor quality weld rod and perhaps workmanship from the welding, and that may be associated. You could draw a line that's associated with limited requirements related to those two components in the design documents. What did the design require with relation to weld rod and welding installation requirements? So then a series of repairs was undertaken under the presence of a WSP engineer in a sort of a pseudo CQA engineer role that we described in the earlier slide. The pond was then filled. No leaks have been reported, which is good news. It means that a reasonable job's been done of that repairs. But what we don't really know is how long this liner system's going to last. What's its durability look like? These are fairly challenging exposure conditions, pH1. And as far as we are aware, there was no compatibility testing or durability testing done on the geomembrane that was used in the works for the service condition. So we don't know how long this liner system is going to perform. So there's a fairly high degree of uncertainty and a fairly significant risk for the owner that they might have to take this pond out of service again in the future, which obviously has significant impacts on the mine and revenue generation by the mine, and therefore can be very costly for the mine, and perhaps is a good example of the benefits of, or the increased level of confidence that durability testing that can provide you and help reduce the likelihood of these type of risks being prevalent. So anyway, fingers crossed they were third time lucky. Another example. So this is for bauxite residue storage. So bauxite residue, most of the time, is a result of the Bayer alumina refinery process. So it results in a very caustic or high pH residue, which is the bauxite residue, which requires storing. And so this facility was in a remote desert environment with lots of sand, no clay, which is what you might expect in that environment, and no nearby water source. But there was a requirement for a composite liner to be incorporated in the design to protect the environment, which is common for these type of applications. There was an approved feasibility stage design that included a HDPE geomembrane and a 1 metre thick clay liner to form that composite liner. I'm not sure if anyone can see a problem or a challenge there associated with that feasibility stage design. So WSP were engaged at the detailed design stage, and we developed a liner system that incorporated a GCL, geosynthetic clay liner, in lieu of a 1 metre compacted clay liner. We did engineer analysis and seepage assessment to help demonstrate the efficacy of that design compared with a clay liner. And we went to an independent durability testing regime for the GCL and the geomembrane, in the same type of process we spoke about earlier. And that was undertaken on candidate products that were nominated by suppliers, and those suppliers nominated them with an understanding of what the service conditions were, and they nominated what might be called high performance geomembrane and GCL products. And the testing was done with liquor samples supplied by the client. You can see the samples of the liquor in the photo on the bottom right. The results of the testing returned varied results for different materials, and some products were what we would say were definitely not suitable for the application based on the results of the testing, but we were able to identify HDPE and GCL products that were considered appropriate for the application based on the results of that testing. So then we got to construction, and we developed a design that included a robust QA/QC regime related to material supply and installation. So that included the MQC stage, the independent quality control testing done at a third-party laboratory, and that included sampling from the factory and also specialist deformulation or fingerprint testing on the geomembrane to identify if the supplied material had the same stabilizers and additives as the sample provided for the durability testing. So checking that what got delivered to site had the same properties of the material that went through the durability testing. And then the CQA stage, which included full-time on-site supervision and leak location testing, among numerous other requirements. It was successfully constructed, and in this situation, the use of the GCL in lieu of the compacted clay was assessed to result in a more sustainable outcome. So just expanding a little bit on that, there's a white paper that's been prepared by GSI, White Paper 41, which there's a screenshot of it there, which outlines a methodology for assessing sustainability for traditional materials versus geosynthetics. And I guess I won't go through the numbers, but based on indicative calculations and very indicative, it looks like there might have been in the order of a 90% or greater greenhouse gas emissions saving resulted from using the GCL than a clay, and that's primarily driven by the haul distance for the clay. That's the main factor there. If you're hauling clay a significant distance, then most of the time, or all the time, the GCL is going to be have a lower carbon footprint than the clay, but obviously that's case by case. And the other factor that is important is that by using the GCL, we're able to significantly reduce the water demand, which obviously in this part of the world was significant impact or cost. The clay, if you're constructing with clay, the clay needs to be moisture conditioned and constructed to at least optimum moisture content to perform as a clay liner, whereas the GCL had reduced moisture requirements. So, so a really positive outcome in that regard. So just, to finish up with the summary, geosynthetics can be part of engineering solutions to manage and mitigate impacts of the environment from mining. They may offer increased performance than conventional materials, obviously application specific, and similarly may offer reduced greenhouse gas emission alternative than conventional materials. I'm conscious this presentation sort of focused a lot on GCL and geomembranes, but you could sort of go through similar assessments for geonets and geotextiles for those type of applications compared with conventional materials, gravel, sand, etc. Geosynthetics require rigour in design, particularly for high-risk applications. such as those what you're routinely dealing with in the mining industry. So that's obviously, there needs to be strong focus, and an experienced designer needs to be involved. And often result in improved sustainability outcomes for projects. So that was all I had. Thank you very much. Ryan will present next.
Thank you, Darren, for your presentation. I'd now like to welcome our second speaker, Ryan Hackney. Ryan is an environmental solutions specialist at Geofabrics Australasia and has more than 16 years of geosynthetic testing, analysis, development and applications expertise. Ryan is passionate about the role geosynthetics play in the protection of the environment and how these construction materials can be used as an economical and sustainable alternative to traditional construction methods. Ryan has a bachelor's degree in geological sciences and a master's degree in engineering geology, obtained at the University of Leeds in the UK. He is the past secretary and current treasurer of the Australasian chapter of the International Geosynthetic Society. Please welcome Ryan Hackney.
Hello and welcome to today's webinar on geosynthetics and ESG compliance in mining. My name is Ryan Hackney and I'm the Environmental Solutions Specialist here at Geofabrics. So for those in the audience that are not as familiar with geosynthetics, here's a general description of a geosynthetic. So a geosynthetic, it's a general term describing a product, at least of one of whose components is made from a synthetic or natural polymer. And they come in the form of a sheet, strip, or a three-dimensional structure. And they are used in contact with soil or other materials in geotechnical and civil engineering applications. In terms of the geosynthetic types, there are a range of different geosynthetic materials. This table highlights some of the main ones, and that includes geotextiles, geosynthetic barriers, geogrids, geocomposites, geonets, clay geosynthetic barriers, geocells, and geomats. And in terms of the functions that geosynthetics can provide, those geosynthetic types, geogrids, geotextiles, geomembranes, they can perform either one or more than one function when utilized on a project. So those geosynthetic functions include a barrier function, a drainage function, filtration, protection, reinforcement, stabilization, separation, or erosion control. And as I say, one of these geosynthetic types may encompass more than one function. So for example, within the geotextile type, there can be a variety of different geotextiles, which can be their manufactured methodology or their polymer type, and different gradings, which could include a range of mass per unit areas. And the subgroups of those geotextile types can result in those different geosynthetic functions that can be performed. Just to highlight some geosynthetics in action, I've got a few photographs on the following slides. So this slide shows you the construction of a waste containment cell. So this is an engineered void in the ground. The subgrade soil has been prepared and compacted in an engineered manner to a specific specification, and then on top of that subgrade is a geosynthetic clay liner that has been deployed that you can see there. Those geosynthetic clay liners are overlapped by a 300mm width. And then on the slopes there at the side, you can see a white material. So that white material is actually a white geomembrane. And that white geomembrane, again, that's been deployed over a geosynthetic clay liner, which you can't see because it's been covered. But that geomembrane is typically welded, and the overlaps on the GCL and the welds on the geomembrane form that hydraulic seal once the material has been fully deployed across this site. The next slide here, we can see an example of a woven high-strength geotextile that's been deployed over a soft subgrade. And again, you can see on top of that woven material, there's some large angular ballast materials being placed there. And eventually, when this full site has been constructed with the high-strength geotextile, the large rock fill will be placed on that geotextile, and the geotextiles performing a separation and a reinforcement function to prevent that fill being encapsulated by that soft soil beneath. An example here of a geotube. So a geotube is a material that is constructed of a woven fabric. It's essentially a large pillowcase that's tens of meters in circumference and length, and these tubes, these cases, are pumped with a slurry. And the intention of these products is that the solids are retained within the tube, and the liquid or the water escapes out of the pores within that woven geotextile and leaves the solids within the tubes. And we'll see some more discussion examples of that later in this presentation. Here again is another example of a containment cell, and this is just highlighting the fact that, again, geosynthetics are used not in isolation, they're used synergistically with one another, so that can include clay liners and geomembranes and drainage materials that are used together as a system to perform their intended function. And here we've got an example of a geogrid. So in this particular case, this is a stabilizing geogrid. We can see an angular aggregate being placed over the top of the grid. And by utilizing the geogrid in these types of applications, you can actually reduce the depth of that overburden rock by using this geogrid to stiffen the whole layer. Okay, so I'd like to just touch on the United Nations Sustainable Development Goals. And these United Nations Sustainable Development Goals are global goals, and they were adopted by the United Nations in 2015 as a universal call to action to end poverty, to protect the planet, and ensure that by 2030 all people enjoy peace and prosperity. The 17 Sustainable Development Goals are integrated, so one action in one area will affect the outcomes in another, and that the development must balance social, economic, and environmental sustainability. And the reference I have on the screen there is a paper, Healing the World, a Geosynthetic Solution. And this paper actually outlines the role of geosynthetics and how they can address all 17 of these United Nations Sustainable Development Goals. But in today's presentation, I'm going to focus on just a few select goals and how geosynthetics can help achieve those goals. I'm going to start with environmental protection. So, in the application of mining, there are various different stages of the mine, and within those stages, we have various constructions that occur to either contain or divert or store mining materials. So some examples include mine waste storage, where we can utilize cell lining systems, or we can cap waste storage. We have heap leaching facilities, tailings dams, evaporation ponds, and it can be an effect on the environment from these facilities and the materials that they're holding. So some examples here on the screen include the effect on the environment can be impacted from acid and metalliferous drainage. We can have elevated sulfates and salts. We can have radioactive materials that can impact on the environment. We have sulfuric acid solutions that can be part of metals processing. We can have hypersaline chemistries as a result of coal seam gas extraction, for example. We can have high alkalinity leachates, such as in bauxite refineries. We can have elevated sodium concentrations and metal concentrations. And we can have free cyanides in heap leaching facilities, such as processing gold, for example. So in terms of being able to protect the environment from these various chemistries that are a result of the mining process, there are geosynthetic materials that are utilized to protect the environment. So I'm going to going to give a few examples of two of these barriers that can be used either in isolation or as a system in protecting the environment. One example of which is a GCL, which is a geosynthetic clay liner. And a geosynthetic clay liner is a manufactured liquid or gas or gas barrier, and it's comprised of a bentonite clay core, and that clay bentonite core is sandwiched between two synthetic geotextiles. And those geotextiles are needle punched and typically thermally locked together. And that needle punching process provides internal reinforcement to the GCL so that the material is actually stable on slopes, because bentonite alone has a very low shear strength. So bentonite clay, it's manufactured in a dry state, but it swells to many times its dry volume once it uptakes moisture from the surrounding environment. And in its hydrated state, and when it's confined, it has a extremely low level of permeability to water, but also to other chemistry, so as you'll see in the next slide. Here in Australia, GCLs are manufactured in rolls that are 4.7 meters wide, and they can be manufactured in any desired length, but typically up to 80 meters. And they are rolled out on site and overlapped like you saw in those previous photographs. And that overlap section is 300 millimeters width. That creates a hydraulic seal. Typical applications for GCLs include basal liners, caps, funds, ponds, and water storages. GCLs, they're often used in composite liners, which also include a geomembrane as primary containment, but in fact, GCLs can also be used themselves as a primary barrier, depending on the chemistry and the site-specific situation. So, how do we measure the effectiveness of or the performance of geosynthetic clay liner? We test that in our research and development laboratory. And what we do is we perform a triaxial permeability test, and we actually hydrate and permeate the geosynthetic clay liner with the chemistry of concern. So here you've got an example of different levels of hydraulic conductivity that are achieved over time with these different potential mining chemistries. And here you can see there's examples of hyperalkaline fluids, various salts, sodium hydroxides, and even hydrocarbons and seawater. And you can see from that hydraulic conductivity chart, there are a range of hydraulic conductivities that can be achieved over a few orders of magnitude, but essentially, even at the most aggressive chemistry, we can still achieve greater than 1 × 10⁻⁹ meters per second hydraulic conductivity when permeated with a hyperalkaline liquid, for example. Again, we can modify a geosynthetic clay liner by incorporating other additives. This can include polymers, it can include ion exchange resins, it can include powders such as activated carbon. One such example here is the incorporation of activated carbon and polymers into the geosynthetic clay liner. And this gives the GCL an additional function. So as well as functioning as a low permeability barrier, the addition of activated carbon, for example, can absorb contaminants such as per and polyfluoroalkyl substances, but also it can entrap free cyanides as well. So activated carbon is known to absorb free cyanide. So again, by incorporating other additives into a geosynthetic clay liner with the bentonite, we can have additional functions that can be achieved through that process. Moving on to geomembranes. So geomembranes are typically a primary barrier that's used in containment, and usually the first line of defense in protecting the surrounding environment from contaminants. There are a large range of geomembrane types, and this table on the right hand side of the slides gives a breakdown of the different types of geomembranes, and these include both thermoplastic geomembranes and thermoset geomembranes, or a combination thereof. Geomembranes are a flexible polymeric sheet, and they're typically used, as I say, as liquid and vapor barriers. And the bottom right-hand section of the slide there gives you a bit of a breakdown in terms of the percentages of the different geomembrane types and the percentage of use globally. And as you can see, the polyethylene family, the high density and linear low density polyethylenes, if we combine those as the polyethylene family, account for over 65% of the geomembranes that are used globally. So I'll take a little bit of focus on that. So with polyethylene geomembranes, as I mentioned, they're the most widely used polymer in the group of geomembranes, and HDPE, which is high density polyethylene, and LLDPE, which is linear low density polyethylene, they're the two main geomembrane subgroups of that polyethylene family. And it's defined, the difference between the high density and the low density is defined by its density, which is that cutoff point, or that specific density is 0.940 grams per cubic centimeter. So anything less than 0.94 grams per cubic centimeter is classified as a low density polyethylene, and anything higher than 0.94 grams per centimeter cubed is classified as a high density polyethylene. So the geomembrane itself, the polyethylene geomembrane itself, it's actually a formulation, and it includes a polyethylene base resin, and then there are additives that are added to that to create a geomembrane. So the additives, they include carbon black. When you see a black geomembrane, that's a result of the addition of 2 to 3% carbon black in the formulation. Or in the case of white geomembranes, it's the titanium dioxide pigment that colors the geomembrane white. In addition to those additives, we have stabilizers and antioxidants. And those stabilizers and antioxidants actually protect that base resin from degradation. And again, on the next slide, we'll look into how we challenge the membranes to be sure of the service life in these different mining chemistries. The geomembranes have different surface finishing, so they can be smooth, they can be textured, or they can be monotextured, which means it's just textured on one side and smooth on the other. And the membranes, they can be monolithic or co-extruded. So that means we can have the combination of both a black and white layer if we co-extrude those layers together. And I just want to note here that not all HDPE and LLDPs are the same. So there's a huge variety of base resins that are available, a huge variety of stabilizers and antioxidants, and the formulation of the mix of those can result in a huge range of different polyethylenes in terms of quality and performance. The reason why we use polyethylenes, essentially, it's very good in terms of chemical resistance. You can see on the table on the bottom there. Very good in terms of resistance to acids, alcohols, and bases. But there's limited resistance in terms of hydrocarbons and oxidizing agents. In terms of the density, there are the effects on the density, effective density on the polyethylene properties. So, for example, as the density increases, the crystallinity increases. That means that we get an increase in tensile strength, stiffness, an increase in chemical resistance, and an increase in abrasion resistance. But with an increase in that density and an increase in that crystallinity, it can also have an impact on its stress crack resistance. So that the more crystalline a material is, the more susceptible it can be to stress cracking. And that can be ultimately how geomembranes fail in situ. So in terms of being able to measure the performance of geomembranes, similar to like I demonstrated with GCLs, we perform what's called an immersion test. So we take the chemistry from the site, the leachate or the liquor or the pore water, and we immerse the geomembrane in that actual liquid. And we do that at elevated temperatures, and that accelerates degradation reactions. And typically what's happening is the chemistry is reacting with those stabilizers and antioxidants. So those antioxidants and stabilizers are protecting that base resin from breaking down. So it's really important to understand the effectiveness of those additive packages and we can measure that by a property such as measuring the oxidative induction time. So we can immerse the material in these liquids of concern, and then at various time periods of immersion, we can take a sample and measure what the oxidative induction time is, and that will tell us how effective that package is over time. In addition to measuring the durability in this way, we can also oven age the sample. So again, this is a hot air oven, and again, it's a challenge of that stabilization package and how well it can protect that base resin. And further performance tests include strain cushioning, which I will speak about in the next slide. So geotextiles, moving on to geotextiles, as I mentioned, geotextiles can perform various functions. Those various functions can include separation, protection, drainage, reinforcement, and it comes down to how those geotextiles are actually constructed. So there's different methodologies such as a woven geotextile, a knitted geotextile, a non-woven geotextile. And within that non-woven category, we can again go into another subcategory of non-wovens, which include needle punch, spun bond, heat set, staple fibers, and continuous filament. And the various different manufacturing methodologies can lead to those different functions that the geotextile can perform. If we focus on cushioning, in terms of protecting that geomembrane that's used for containment, we use what's called a cushion geotextile. And this is a heavier grade geotextile, typically a heavy grade staple fiber. And this sits within the system, typically next to the geomembrane liner, and it cushions the effect of a drainage aggregate or an aggregate material that can impose stresses onto the underlying geomembrane. So we can measure this in the laboratory by setting up this system in the lab, by taking a drainage aggregate material and then placing that on a geomembrane with the cushion geotextile sitting between the two, as it would on site. And then within that system, we have what we call an aluminium recording plate. You can see a picture of that in the middle. We impose the load that this system is going to be subjected to on site. And after a 24-hour period, we can then remove that aluminium sheet, which records those indentations of that aggregate under load. We can laser scan the aluminium sheet, which measures deformations every square millimeter. And then from that, we can calculate the maximum strain that's being imposed on that membrane. So if the strain's too high, we know that we need to have a heavier cushion geotextile, whereas if the strain is lower than the desired strain percentage that's being specified, we can either keep that as a factor of safety, or we can maybe tune the system and maybe try a lighter geotextile. Moving on to geotubes. So geotubes, we've seen examples of those previously. They are used to dewater waste and contaminated sediments. The geotextile containers, they're geotextile containers, and they capture slurry while they allow water to discharge out of the pores, and the solids are remained within the tube, and the water is discharged, and the whole intention is to end up with a spadable cake within the tube. The slurries, the geotubes, they are pumped with the wet slurries via a manifold and a series of lay flat hoses, and we typically incorporate flocculants and coagulants into this process before the slurry gets into the tube, and that helps to more quickly evacuate the water out of the pore space. So the advantage of geotubes is that we can process high volumes on a smaller square meter footprint. We can use the water that's being discharged out of the tubes, so that can go back into the process, as water, as we know, is a finite resource. Scaling allows for high flows. We can achieve rapid dewatering, as I say, with the addition of flocculants into the process, with up to 99% of the solids that can be retained. By encapsulating the solids in the tube, we can prevent rehydration if there's a weather event. The tubes, because they're encapsulating the solids, it mitigates airborne dust issues. There's a low carbon footprint, as an example I will show shortly, and reduced odor. There's some cases where odor can be an issue, and by encapsulating the solids, we can reduce odor. In terms of rehabilitation and revegetation, one product range that's available are erosion control products, and these can be synthetic or natural geotextiles typically. And we can do analysis on these type of products to show how they can perform in terms of their effectiveness of erosion control. And there's unvegetated tests where we can look at different rainfall intensities and measure the soil loss underneath the material to show the effectiveness of the product in an unvegetated state. Or we can show the effectiveness of these erosion control products once they've been vegetated and show at various levels of velocity what the soil loss looks like underneath the product. And as I say, some products perform really well in terms of once they've been vegetated, reducing soil loss to a very high degree. A few slides on the decarbonisation with geosynthetics and life cycle assessments. So life cycle assessments of a geosynthetic include these various boundaries, and this allows us to measure and calculate the embodied carbon within a geosynthetic material. And then by having that information, you can then incorporate that into carbon footprint calculations, because there are published values on traditional materials in terms of their embodied carbon, and there are published values in terms of geosynthetics and their embodied carbon. And these life cycle assessments can include the various stages of a geosynthetics life cycle. So that can include anywhere from raw material extraction through to manufacturing into a geosynthetic product, and then transportation of that product to the project site, the energy required in constructing the actual project itself with the geosynthetic material, and then the ongoing operation and potentially the disposal at the end of the project. So by taking various measurements and calculations through these boundaries, this is how we can measure these embodied carbon values of geosynthetic materials. There's a GRI white paper 44 and the references for this at the end, but the white paper shows that by incorporating geosynthetics into a design over a traditional construction methodology, on average can result in 65% carbon savings. So there's a lot more information available on this, and please get in touch with me if you would like to share some of this further information. A few examples in terms of stabilization. There's a haul road here that's theoretically constructed 5,000 square meters. By incorporating stabilization grids, we can reduce this non-stabilized layer from 970 millimeters to 455 millimeters, and that has benefits in terms of not just cost or time, but there's significant carbon savings in the reduction of truck movements required for moving that extra aggregate layer. Geotube, the alternate methodologies can include a belt filter press, which includes a lot of energy in terms of motors and mechanical dewatering. In this example here, the Geotube has a lower embodied carbon of 153 tons per CO2 when we use the same volume of sludge on the same site by comparing both the Geotube technology compared to a mechanical dewatering technology. Channel lining, so if we compare a traditional concrete poured channel versus a geosynthetic concrete canvas matting, by utilizing a geosynthetic concrete mat in place of a poured concrete, again, this example shows that there is a 60% lower global warming potential by utilizing this geosynthetic solution to construct a channel. And then when we look at geosynthetic clay liners versus a traditional compacted clay layer, and this purely just looks at the CO2 in terms of the truck movements alone. So if we take the example of a 1 hectare site, and the example that there's a 10 millimeter distance to the clay borrow pit and a 1,000 kilometer distance to the geofabrics plant, there is over 0.5% in CO2 savings in transport alone from moving 2 trucks of GCL to cover the same footprint rather than 470 trucks to move the same required volume of clay to achieve that same low level of hydraulic conductivity. Last 2 slides, just to highlight by choosing local, geosynthetic materials by Geofabrics are manufactured in 2 plants, one in Albury, one in Ormo. That has environmental benefits alone in terms of carbon footprint and transporting distance from the point of manufacture to site, but also by choosing local manufacturing. Geofabrics, they employ over 100 production staff across those 2 production sites, and that contributes over 10 million per year into regional communities, but also supports over 1,000 active suppliers in regional Australia. And in terms of incorporating recycled material into geosynthetics, so Geofabrics manufacture geotextiles and HDPE pipe with recycled content, and that has resulted in the diversion of over 70 million plastic bottles from landfill that are now incorporated into geosynthetic products that can be utilised on construction projects. Here's a table of references, and thank you for your time today.
Thank you. It's thank you to our speakers this afternoon, Ryan Hackney and Darren Webb. As always, it's now your turn to get involved, and if you could please ask our speakers questions via the YouTube chat box and who your question is directed to. A big thank you to everyone who submitted questions whilst registering also. And we might start off with you, Ryan, and we've had a question that's come in from Alistair. And Alistair is watching from Canberra. Good afternoon to you, Alistair. Asking Ryan, does Geofabrics use a model or models to predict the effects of geosynthetic engineered solutions and associated ESG benefits for the client and environment? If yes, I'd love to see details on the models, hear about details on the models. Thanks, Ryan.
Thanks, Amanda. Okay, yeah, thanks, Alistair. And to answer your question, yes, Geofabrics have some specific software that we're using. And initially, we're using that software to conduct life cycle assessments of the products that we actually manufacture. So, as we said in the presentation, I talk about the various boundaries of products, and that includes, cradle to grave. So, those boundaries is where we measure the embodied carbon of a geosynthetic product. So, over the coming year, during 2024, you will see environmental product declarations being published by Geofabrics, which gives you the environmental impact of the of some of the geosynthetics we manufacture. So once we have those values and numbers, we also can use that similar software to assist in looking at carbon footprints of the projects as a whole. So we can model what that looks like in terms of taking what the embodied carbon is of the geosynthetic material, and then add to that the transportation from manufacturing plant to site. We can work with you in terms of what type of plant are being utilised to deploy that material on site, and then if we want to look at it from a cradle to grave perspective at the end of life of the asset, we can make some predictions in terms of how the materials either recovered and recycled or disposed of. And from that, we can have a full model in terms of what that carbon footprint or life cycle is of the project as a whole. So we're happy to work with you on those as a project by project basis. Just get in touch. Thank you.
Thank you. Thank you for that great answer. And Ryan, I might just stick with you for this next question, which is from Pradeep. And Pradeep is watching in Queensland. Good afternoon. Asking you, Ryan, how can it help in electric supply substations? Ryan.
Okay. In terms of geosynthetic solutions there, I think it's going to depend on the site specifics. it could be that a substation's in a remote location and that access could be a problem. So there's various geosynthetics that can be used to help with access over poor ground, for example. There's showcased a photo of a high-strength woven geotextile product that can be utilised over soft ground. That could be one example, but geogrids can be used to stabilise soft ground if access is an issue. I guess another area in substations that where geosynthetics could be utilised could be drainage. You know, there's usually some drainage element there that may need to be accounted for. So you can use products such as geonets and geocomposites, or even geopipes that can be used to collect and divert water if it could be a water problem. So it's really going to depend on the site specifics of the and what the actual issue is that you're wanting to resolve. But by all means, get in touch with us and we can look at your project and offer a solution as required.
Thank you for that, Ryan. Darren, bringing you into the discussion. We've had a question, Darren. How are leaks monitored, collected in the example of the geomembrane lined acid storage pond? Darren.
Thanks, Amanda. Yeah, so that pond, and I guess, this is typical of most ponds of this type of situation, included an underliner drainage system. So leaks are collected via that system, and that reports to a sump where the leaks can be extracted, and that enables the leakage rate to be monitored. It's important to sort of talk about that a little bit because having a system like that is critical to the performance of a liner system, an exposed liner system where you're storing a liquid. The reason for that is, and I think this is in the context of a HDPE geomembrane, I should clarify. So HDPE, as Ryan indicated, the density of that is 0.94 grams per centimetre squared approximately, and this is probably any polyethylene geomembrane is less dense than water, and so in the event that you have leak through a hole in the geomembrane, the liner will begin to float because it is less dense than the liquid it's storing, and then if that leakage is not drained, the flotation will increase over time as the leakage rate continues, and then ultimately that you end up in a situation where the liner is not performing as intended. It's effectively failing, and that's why drainage systems like that are routinely included in lined ponds. The other approach to counteract that issue is confining the geomembrane, so putting something on top of it to hold it down. So it is those underliner drainage systems are very important for ponds like that.
Thank you for that, Darren. And Ryan, coming back to you, and maybe Darren, you could also pick up on this one. We've had a question coming from Bruce in New South Wales, asking you, Ryan and Darren, what is a realistic lifetime to assume for a PE liner containing brine or dried salt? Starting with you, Ryan.
Yeah, okay. So first you need to look at the chemistry of the brine and the salt. But once you've looked at that and the concentrations of the salts themselves are probably or are fairly compatible with polyethylenes. So it's the detrimental effect, I think, is with brine solutions or hyperbrine solutions, they tend to have raised alkalinity. So with those raised alkaline conditions, that's what can start to degrade the geomembrane, the polyethylene. And as I mentioned in my presentation, the polyethylene is a formulation. So as well as the polyethylene resin, it includes the stabilizers, it includes antioxidants, and it's really important to have that right package that's compatible with the brine and this higher alkaline environment. So the alkalinity can can be what breaks down that stabilizer package. So as I mentioned, there's many different types of stabilizers available, and it's choosing a stabilizer or relying on the manufacturer to have the appropriate package with the brine chemistry. So, as I mentioned again in the presentation, we can assess these, and Darren mentioned this as well. You can assess various different geomembranes by conducting performance testing. So that's what would happen in this situation with the brine. We would take the brine of interest, we would take samples of the brine, or we can sometimes synthesize the brine in the laboratory as well. And then we can do the performance testing. So the performance testing will include submerging the membrane of interest in that brine material, measuring how it ages over time, so we can measure how the stabilizers and the antioxidants deplete over time. We can look at other properties of the polyethylene, such as the tensile strength and the stress crack resistance over time. And by monitoring these at various different temperatures, we can do what's called arenas modeling. So by accelerating the reactions, by increasing the temperature, we can then predict how long the materials can last in situ at a service temperature. So a general rule of thumb that you can take is that for every 10 degrees Celsius increase in temperature, you can double the rate of reaction. So when we do these immersion tests, we operate at higher temperatures, such as 60 degrees, 75 degrees, 85 degrees Celsius, and that's speeding up that reaction process, so that then if you have a liner that's at a service temperature of, say, 30 degrees Celsius or 20 degrees Celsius, we can do that Arrhenius plot and regression and understand what the service life of that liner would be by doing those elevated temperature tests. And just to give you an example, in terms of brines and polyethylenes, we have assessed and used polyethylenes in brine ponds for coal seam gas, and we've qualified products, a certain formulation of polyethylene product for service lives in excess of 30 years, just for example. But it's just about choosing the right product and undertaking those durability assessments to be sure of that service life. Hope that answers the question in part.
Yeah, thank you, Ryan. Darren, do you want to add to that?
Well, look, I probably don't have too much to add. I think Ryan's covered it. That there's not an answer to that question. How long will it last? You need to go through the process to understand if it's really critical for your application to know that it is going to last. I expect for most applications that would be the case. You want to know how long your design's going to last. But yeah, look, from experience, you're in challenging applications like that. If it's exposed, which they tend to be, if it's covered, then that really helps. It lasts longer. But if it's exposed, 20, 30 years is probably a good outcome.
Thank you. Thanks for that, Darren. Thanks. Ryan, a question coming from Mohammed here in Victoria, asking you, Ryan, how much ahead has Australia overcome some of the challenges to develop a geosynthetic products that incorporate recycled content among other compared to other developed countries? Thank you, Mohammed. Great question. Ryan.
Yeah, good question. So just to give you some background, Geofabrics have now been supplying geotextiles and geopipe for a number of years now, and those products include Australian recycled content. So in 2020, Geofabrics launched a range of geotextiles called Bidham Green, and Bidham Green is a polyester continuous filament geotextile manufactured in Albury, and that geotextile incorporates Australian recycled polyester content. Similarly, we have a pipe called Megaflow that's used for drainage applications, and again, that's incorporates recycled HDPE content. just to give you an example, and I think I mentioned it in the last slide there, since that launch in 2020, we've now diverted over 70 million bottles of that would have traditionally gone to landfill that are now incorporated into geosynthetic products such as Bidem. There's other products within the Bidem range, such as Tractex, which is a geotextile used for mud pumping in the rail industry. There's a geotextile widely used in road for reflective cracking called Sealmat Green. Again, includes recycled content. EnduraSeal Green, which is it incorporates a membrane and it's used as a impermeable layer in certain applications. And as well as the geosynthetic materials itself, it's important to note that the wrap and the core in some materials that we supply also include recycled content. So I hope that answers that question for you.
Thank you. Thanks, Ryan, for that. James has sent a question into you, Darren. Good afternoon to you, James, asking Darren, how high is the risk of a GCL drying out when it's not constantly exposed to liquid? And Jen goes on to say, are GCLs self-healing? Darren. Okay. Hi, Brian. I just had a question for you. Darren, have you got sorted out?
Sorry, what was that, Amanda?
Oh, that was all right. Sorry, Darren. We just lost the audio for a minute or so.
Okay.
Do you mind starting answering that question again?
Yeah.
Thank you.
Yep. So GCLs need to be hydrated. They need to be moist to function and provide the low permeability that you'll be looking for by specifying a GCL. So how do you ensure that happens? Often they're used in conjunction with the geomembrane in a composite lining system. So the geomembrane is a barrier to help stop it drying out. They also need to be confined. And ultimately, they're receiving their moisture from the subgrade normally. So the subgrade needs to be moist to provide the moisture for the GCL to uptake and then maintain its hydrated condition. So having an exposed GCL where it's not confined or not covered, or both, it will be subject to drying and likely will not perform in the manner that the design's looking for.
Thank you for that, Darren. Brian, a question we've had coming in asking you, does the more crystalline poly fail early due to cracking, or does this occur due to fatigue over time? Thanks, Ryan.
Okay, so I think the question, it relates to polyethylenes and the increase in crystalline that I was talking about. High density polyethylenes are more crystalline than low density polyethylenes. This is why you'll see on high density polyethylene specifications a property called stress crack resistance specified and nominated for the product. And the stress crack resistance is a resin property. So this is where it's appropriate to be aware of the fact that not all polyethylenes, not all HDPs are the same. So different manufacturers will use different resins, and the different resins will ultimately have different stress crack resistances. So there are polyethylenes on the market now that have really high levels of stress crack resistance. Darren pointed out GRI GM13 specification for HDPE geomembranes. For general applications, in that specification, the stress crack resistance is currently a minimum of 500 hours. So this is a property where the geomembrane is subjected to a small crack that's imposed in the membrane in the laboratory, 20% of the material thickness. A load is then applied to that geomembrane, which is equal to 30% of its yield stress. And then that load is sustained on the geomembrane until that notch propagates and the material cracks. And that's how we measure the stress crack resistance. So that 500 hours in the GRI GM13 specification for general applications is what's stated, but there are polyethylene geomembranes on the market and available now that have stress crack resistances in the range of greater than 3,000 hours. So I think it's just key to highlight that, again, not all polyethylenes are the same. There's different resins that are used, and they all have different levels of stress crack resistance. So it's just something you can usually check on a technical data sheet that will give you that information.
Thank you for that, Ryan. Darren, I just wanted to bring you in. We've had a great question coming in asking you, plastics polymers are getting a bad rap at the moment. Have your clients voiced concerns about potential PFS on their sites? And how does it factor into your environmental assessments? Big question, Darren.
So there's two parts to that question. I'll answer the second part first. So PFAS and PFAS related substances are basically everywhere is what the research shows. It's in different concentrations and in higher concentrations in higher risk areas like firefighting grounds, airports, etc. And the interaction between, well, if you're trying to safely contain a PFAS impacted material, then you need to consider the impact that will have on the liner system in the manner that has been discussed in both Ryan and my presentations. So there are geomembranes that contain PFAS. You need to go through the process of assessing which geomembrane is appropriate for your site, considering all your site-specific factors. So that's the answer to the second part of the question. The first part was around plastics and polymers having a bad rap. I'm sort of inferring that question might be related to the microplastics issue that's routinely in the media at the moment. These polymers, microplastics occur when polymers or plastics degrade. Okay, so these geosynthetic materials, if they're appropriately designed, so that's a big if, and they're a quality manufactured product, they will last for a very long time, much longer than most plastic materials that are floating around in society. So it's something that you can consider, but there is some research that's been done on microplastics and the geosynthetics industry and geosynthetic materials. I'm not going to try and summarise that research, those publications. You can go and have a look, read those for yourself, make your own assessment. But I guess these geosynthetic products can last a very, very long time.
Thank you for that, Darren. And we are running out of time, and I just thought it's a good way. We've covered a lot today. If you could just, starting with you, Darren, if you could just quickly summarise in, say, less than a minute, the key messages from your presentation you want to leave our audience with today. And then, Ryan, if you can do the same. Thank you. Darren.
Look, I think my message would be geosynthetics can be very useful and can offer really great solutions to the engineering industry and the mining sector, but they need to be designed, or the designs using them need to be undertaken properly and carefully.
Yeah, thanks, Darren. And yeah, I'd probably mirror that thought. And again, geosynthetics, they have significant environmental benefits over traditional construction methodologies. It's now measurable by looking at EPDs, life cycle assessments, carbon footprints. We can actually put numbers to what that looks like now in terms of utilizing geosynthetics in construction compared to traditional methodologies. So sustainable outcomes can be achieved with geosynthetic materials. And as I say, that's measurable and we can assign values to that. So that's my key takeaway there. Thank you.
Thank you for that, Ryan. And it is all we have time for today, which today has been our first Thought Leaders webinar for 2024. So thank you to everyone for watching and registering. Please join me once again in thanking Darren Webb and Ryan Hackney for great presentations and taking the time to do this today. I'd also like to thank Engineers Australia's industry partner, Geofabrics, for their ongoing support. As always, we're looking for ways to improve and plan for future sessions. So if you could take 2 minutes to complete a short feedback form, which is linked in the description box below. Thank you again for joining us, and I look forward to seeing you at our next Thought Leaders event. Thank you and good afternoon.